so much for inviting me here. I am like pumped beyond words. Like I can't even, like I'm not even caffeinated. I'm just like, yes. So thank you. Again, my name is Raquel Vèlez. You can find me on Twitter. I'm Rockbot. It's like Rocky and a robot. That's me, Rockbot. And I work at Storify. I'm a front-end engineer at Storify. If you want to learn more about social media and journalism and all that stuff, I'm happy to talk about that. Or we could talk about robots. Is there something wrong? No? Oh, OK. So let's get started. First of all, so warning, there may be math. There will be math. If any of you have an allergic reaction to math the way that I have an allergic reaction to space, it's OK. Just hold out. Like, bear with me. It will get awesome. I promise. And there will be a demo. So yeah, OK. So a little bit about me. I have been a practicing roboticist for about 10 years now. Believe it or not, before I went into robotics, I wanted to be a filmmaker. My whole goal in life was to be the next Steven Spielberg and move out to California and win an Academy Award and be just super awesome. But then I was a high school student, and I got invited to a Society of Women Engineers event in Princeton University. And there were a bunch of engineers, and there was this one mechanical engineer who's like, yeah, these engineers are all really awesome, whatever, great. But I built this in my class. And she whips out this robot and puts it on a table. And I was like, oh my God. I learned 3 things that day. First, that it is possible to build robots. I didn't know that. I thought that robots were just figments of our imagination that we saw in movies and on TV and read about it in books. And then the second thing I learned was that women could build robots, because that also didn't occur to me. And then third was that I already had the skill set that I needed to get started. And that just completely blew my brains. And I just was like, OK, that's it. Film's over. Robots all the time. So I made it my life goal to just start building robots. And my very first robot, I was in high school. And I had a lot of privilege, but I got to build this awesome guy. His name is Adrian. And he is a search and rescue robot. His job is to follow this line and find victims made out of aluminum foil. It was really awesome. It won a couple of awards at different competitions internationally. So if you don't think that you can start playing around with robots, this is a really good starter. Actually, at the time, Lego Mindstorms, how many people have heard of Lego Mindstorms? Excellent. So at the time, and I was 17, 18 years old at that point, it turned out that the average user of Lego Mindstorms was a 34-year-old male. So like anybody can just get started and start playing with robots. So that was high school, and I knew I had to be playing robots for the rest of my life. So I went ahead and just kept going. I went to Caltech to get my mechanical engineering degree. And this was my second robot. Or rather, this was my second robot. This is Bob. This is Caltech's first entry into the DARPA Grand Challenge, which, if you've never heard of that, it's a race for autonomous vehicles in the desert. So basically, driverless cars. You've probably seen them before. But this was one of the first instances of anybody ever actually doing that. And this was my second robot, which is kind of a huge jump between the two. But whatever. It was awesome. And I'd like to note that the reason we had to use a Chevy Tahoe is because the entire back of this vehicle is full of computers. Full of computers. Our iPhones can probably do about half of what that does now, but at the time, it was, oh my God, OK. So during and after college, there were some more robots. Chris mentioned I worked at NASA JPL. I did some DoD stuff. I did an internship in Germany doing biomechanical research using 2 KUKA robots, which I'll get into in a second. And then there are a couple other robots that I can't really talk about. Sorry. But if you want to talk about any of those other robots, just come holler at me. So basically, I was in this world of traditional robotics. And I learned a few things. For example, I learned that robots come from research. It's this really, really slow academic process. And robots are really hard. They're difficult. It's It takes a lot of effort. You have to do, you have to write these papers, and you have to present them, and then you have to hope that nobody else has presented anything like it so that you can get the credit for it. And then you also kind of need your PhD, because PhDs do research. Research costs a lot of money, and they kind of need, and I put this in quotes because I'm debating this, but they need object-oriented programming and threading because of all the vast, vast amounts of sensor data that's coming in. So, whatever. Great. I also learned that if you're wondering about robot domination, not going to happen anytime soon. You're more likely to get hit by a zombie apocalypse than Skynet, just so you know. And if you want to know why, ask me about it later. Or come to the NodeBots event tomorrow, and you'll find out why that's not happening anytime soon. So then I took a little bit of a break from robotics. I was getting a little tired of being alone in a lab, and it was cold, and this whole academic process was really slow. And so I decided to do something that kind of filled my instant gratification thing. And that was web development. I was like, hey, I can press refresh, and boom! I can see what's there, and that's awesome. I don't have to worry about compiling it and then porting it over to the robot and hoping and praying that the robot will still work after everything, and that there isn't like magic smoke or something. I can just literally press refresh and see what happens. But then here I am playing around in Node and having some fun, and then there's this guy, you may have met him, who decided that he wanted to start playing around with hardware and Node, and I was like, okay, that's cool, no big deal. And then there was this other guy, who decided that really robots. Hardware, one, okay. Robots, yeah, okay, cool. And I saw his talk at NodeConf last year, and it was really cute. There was this little robot, and he was running around the stage. He was trying to avoid these obstacles, and I was like, oh. But then I said, wait a second. What if we could do more? What if we could make them smarter? What if we could do stuff? So I did. So I basically have created this module called Vector, which I'll get into a little bit more. And the quick version of it is it's a linear algebra module specifically for robotics, just kind of as a starter. So without further ado, let's get into it. A little bit of Robotics 101, artificial intelligence. Let's talk about what that means. What is artificial intelligence anyway? And really, it's simple. You're giving something else the ability to make decisions. Simple, right? So for example, let's say you have this adorable little robot who's trying to avoid obstacles. You could really program this with a simple if-else sort of thing, right? So if I'm driving along and I see something and I can't go through it, then stop, move back, turn a little bit, and then try again. If I hit something, or am close to something, stop, move back, turn a little bit, and then keep going until I get through away from the obstacles. That is absolutely artificial intelligence. That's called obstacle avoidance. Simple. But what if you need something a little bit more complex? So Robotics 101, again, serial manipulators. Who's heard of a serial manipulator? OK. I promise you probably have all actually seen serial manipulators. You just didn't know that that's what they were called. This is a KUKA robot. It is a serial manipulator. Basically, it has a series of joints connected by links. This particular KUKA robot is writing a version of the Martin Luther Bible. Why? I don't know. Does it matter? Not really. I would like to note that KUKA is a German company, and maybe that has something to do with Martin Luther. I don't know. Anyway, so great. So let's kind of now, OK, guys, the math is going to start. Just brace yourselves. So Want to come? OK. So this is a serial manipulator, once again. You may have seen these in building cars. How many have seen those big robots that kind of piece cars together? Yeah, exactly. That's a serial manipulator. That's all it is. And OK, so the whole point of this is, like I said, there are a series of joints, and they're connected by links. And you have some sort of base, and you have some sort of claw. We're going to call it the end effector, because that's more scientific sounding. Or we can just call it the claw. Let's just call it the claw. OK. So we have a claw end, we have a base end, and each we have a couple of joints. And the way we represent this mathematically is we look at frames of reference. And so each joint, by convention, has a frame of reference. So I'm going to use my arm, because that's also a classic serial manipulator. So we have a shoulder joint, right? And we have an elbow joint, like this. And then we have like a claw, right? And so there are two major pieces of serial manipulators in terms of mathematically doing fun stuff with them. So there's forward kinematics. And the way that forward kinematics works is we have a bunch of inputs that are angles, and then out we get a position. So what does that look like? Each of these joints are angles, right? So I've got my shoulder angle, and I've got my elbow angle, and then I have the position of my claw, right? So basically, forward kinematics says if I put in a bunch of angles, I will get out a position. Does that make sense? Cool? All right. So then that actually has a single solution. Makes sense, right? There's only two inputs. I'm always going to get the same. I'm going to get an output no matter what inputs I put in. It's going to be static. Then there's inverse kinematics, which should be pretty self-explanatory. Basically, we know the position of our claw, and then what are the angles of our joints. And this is a harder problem to solve, because if, for example, I have my claw here, well, I could have my joints in this configuration, or I could have it in this configuration, right? So it's a little bit more difficult. But for right now, we're not going to worry about that. Just understand forward kinematics, inverse kinematics. Make sense? Yep. Cool? All right. Now it's going to get a little bit more mathy. Sorry, guys. So the way that we do this representation of stuff is we use matrices. Matrices are your friend, especially in robotics. They're awesome. I love them. If they scare you, we will clean out the spider webs, and it's going to be fine. It's going to be OK. But the whole point of this is specifically a homogeneous matrix. And the way that it works is we have two major components to it. We have a rotational component and a position component. And so for each frame has a homogeneous matrix associated with it. Okay? So for every single joint, think about it, every single joint has a rotation information and position information. So if I change the angle of my shoulder, the position and the position of my elbow is going to change, right? And then similarly, if I change the angle of my elbow, then the position of my claw is going to change. So you can basically come up with all this information, and now we have a manipulator. Cool? Yeah? I need head bobs, or else I'm just going to be like, OK. So now how do we connect them all together? And it's just some simple chaining. So we have frames for each of our joints. We chain them together, and we get all of our information that we need to go from beginning to end. Cool, right? Yeah? All right. I'm going to pretend you thought that was awesome, too. OK. So now comes vector. We're going to let the computer do all the hard stuff. So we're going to let vector do all of the matrix math. We don't have to worry about, you don't have to worry about how to multiply matrices together, or how to extract position information, or how to define rotational information, or anything like that. We're just going to let vector do it. And I should also note that vector is literally just a linear algebra module. I'm using it for the particular case of a manipulator, but you could also use it for things like computer vision, or game engine graphics, or a whole bunch of other really awesome things, swarm robots, all of that stuff. It can all be used using vector. OK? So like I said, forward kinematics with vector. So we have our crazy matrix. But now with some code, right, you have your homogeneous matrix, you've got your vector, you've got your rotations, and then you have a whole bunch of frames. And so what we're doing is we're just defining each frame as having some rotation and some position. And then we're multiplying it again, each frame to the one before it. And then at the end, we have some position at the end. And this is just forward kinematics. I won't go into inverse kinematics because, yeah. So are we good? Yeah? Give me something. Come on. All right. Thank you. OK. I should note, vector's not perfect. I know that. That's why it's open source. Help. Thanks. All right, so demo time. If this doesn't work, it's going to be OK, because I have a video. But let's see. Hopefully, you can see this. So we're using FaceTime. Yeah. And we're going to turn this on. And OK. Please wake up. Yes. Move the console. Moving it. Oh, damn. We're OK, we're OK, we're OK, we're OK. No, turn. This is what happens. You shouldn't have said anything. OK. How's that? Did it? Wait. Yes. All right. Cool. Can everybody see this, or some version thereof? Can you see the little Johnny 5? OK. So like I said, you have the first joint, which is like a shoulder. And what we can do is we can kind of turn it around like that. Yeah? And then we have our second joint, and we can very carefully do that. And so that's forward kinematics. All I've done is I've put in the input of angles for each joint, and I can see on the screen where the end effector / claw is. Obviously, I don't have a claw in here. It's just a little Johnny 5 sticker. I'll let you guys do the imagination stuff. OK. So yeah, so we've got this. Now, inverse kinematics is a little bit more interesting, right? So I can just kind of grab the end, and I'm calculating mathematically what the angles should be. And so it doesn't even have to be, I could drag it to the end of here and then kind of come back, and it's doing a little dance. The video broke. You see it? All right. Well, anyway, so that's your demo. Thank you. I have another video just in case my backup or my extra backup, or my hardware, my backup hardware didn't work. But anyway, so yes, that was cute, right? So what? So what, indeed. Wait, hold on. I have to fix something. I'm going to turn that off. OK. Try it again. OK. Oh, people are tweeting about me. That's so cute. OK. So great. Except some of you may have Roombas at home. Some of you may have heard about those military drones. Some of you will be playing with NodeCopter tomorrow. Some of you may have heard of Asimo, the Honda robot that can climb stairs and run. Great. That stuff's been solved. This is boring by comparison. So why even bother, right? Why bother with JavaScript robots? And so yeah, fair enough. At this point in time, I really desperately wanted to kind of prove that Node was better than C++ and Python. Either it's not, or I didn't have enough time. I'm not really sure. But we'll leave that question for another day. The fact of the matter is, the traditional robotics industry is kind of done already, right? It's ready. It's well established. It has top tools and funding. The smartest people in the world are working there. Great. And us and our little JavaScript NodeBots, we're just getting started. Fortunately, it doesn't cost that much money. This whole setup probably cost me like $50. But it's a couple of pennies. I don't have $50 million. Although if anybody has $50 million, I will take it. And it's just us, right? It's just us. We don't have PhDs. But we know JavaScript. And I don't know how many of you know Python or C++ or any of the other multiple languages that you could be using, but we all know JavaScript, so let's reframe this, right? So in traditional robotics, there's research and papers, and the reason they have so much money is because it costs so much money. Again, compile, load, boot, hope, pray, magic smoke, oh god, and you have to get a PhD. Whereas in JavaScript community, right, in our little JS community, everything's open source. Forget papers, forget research in top-notch labs, etc. I've just put Vector out there. You can go ahead and use it. Go ahead and fix it. Make it better. That's what we can do. And you just refresh the page. Anytime things don't work, just press refresh. If the server breaks because you overturned it, oops, buy another one for 20 bucks. It's not a big deal. And you don't need to get a PhD. You can just get started. Just get started. Plus, I feel like with our powers combined, without the obstacles of getting a PhD or having to find millions of dollars from the federal government or whatever, yada, 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 we might actually be able to use a new tool to solve complex problems that have been complex forever. Sensor fusion is a really, really difficult problem. That's the idea of having multiple sensors with all these streams of data and then trying to parse it out into something that makes some intelligible sense. We're kind of doing that with big data, right? Why don't we just kind of bring that over to robotics? What if we could solve that problem better than the academics can? I know, scary. OK. But yeah, why not? So go. Build a robot, and then tell me all about it, because I really, really want to know what you guys come up with. Thank you very much.